Swayam Prabha. Digital India. Educated India.
So, welcome back after the break. So, I was discussing about this quantum counter. So, in this quantum counter my aim is to get the corrected emission spectra, right, and then I was discussing about this the measurement of the total emission coming out from a substance where the inner filter effect is highest, right, the complete inner filter effect. So, no excitation light is passing through the sample, right. So, whole excitation light is being absorbed by the sample, the concentration is like so high, and that is the reason for that, and we are going to collect the total emission spectra coming out of this sample, right. Okay. So, now if as discussing, if you now scan this lambda excitation and detect the emission coming out of the sample. Here please note that I do not have any monochromator over here, because I am just interested in the total intensity, right, and the total intensity is coming out to this detector. So, whether the detector efficiency is the same for different wavelength or not, it does not make any sense in this case. So, I do not need to correct the detector response for in this case, right. Okay. So, if I now measure this emission, total emission coming out of this quantum counter, right, as a function of lambda excitation, what I am going to get is this pattern, right, and this is nothing but the spectra of the lamp as I showed over here, right. So, let us name it as L lambda, let us name it as L lambda. So, this is the lamp profile, lamp profile. Now, instead of taking your sample for the emission measurement, let me take some other material in the sample position. What is the material? Is a scattering, like a scatterer. So, scatterer, that scatterer, I will choose the material in such a way that the scattering efficiency is equal for all the wavelength, right, and the substance for that is MgO, magnesium oxide, right. So, I take this scatterer inside my sample chamber, right. So, it is just a scattering, just a Rayleigh scattering, right, just a Rayleigh scattering. So, when this excitation light will fall on this scatterer, this scattering will take place in all the directions almost, and the scattering intensity will also come in this direction, right, scattering intensity will also come in this direction. That means, if I set the wavelength of excitation as lambda 1, I only get the signal in the detector, when the emission monochromator will also set at lambda 1. That means, in this case I will scan this part, this wavelength region, that is my lambda excitation, right. Let me write here lambda 1, lambda 2 to lambda 3. So, I will scan it lambda 1 to lambda 2 lambda 3, this region, and simultaneously I also have to set this value over here lambda 2 lambda 3. That means, synchronous change of wavelength of the excitation monochromator as well as the emission monochromator, right. So, in this case what you will get? You should get this spectra again, right. So, in this detector what you should get? L lambda, but please note here that this detector at a time measuring only one lambda, sometime lambda 1, sometime some lambda between here, then lambda 2, then some lambda between here, then lambda 3. That means, the detector efficiency or monochromator efficiency is coming into the picture, is not it. So, this efficiency is coming into the picture. That means, this observed signal, right, observed signal, I just write output will not going to be equal to L lambda, but it will be equal to L lambda multiplied by the sensitivity of the monochromator and detector together. So, let us name it as S lambda, I have written over here. So, output is L lambda into S lambda. S lambda is the sensitivity of the emission monochromator and the detector, right. So, what you got? You got L lambda S lambda from here, you got only L lambda from here. So, you just divide L lambda S lambda by L lambda, you will get the S lambda, and using that S lambda is nothing but your correction file. But that correction file you will be able to generate. What is the range of this lambda? That range of this lambda will be guided by the absorption spectra of the molecule you have taken in this quantum counter, right. Absorption spectra of the molecule you have taken inside this quantum counter, right. So, for different region of this lambda you should use different molecule. Just for example, over here rotamine B is generally used for this wavelength region. Now, if you want this wavelength region, you need fluorescein. If you want the UV region, you need quinine sulfate, and so on and so forth. There are several quantum counters are available, right. Okay, so, you understand hopefully that how to correct the emissions spectra, right, and whenever you will going to report, if you will use this fluorescence spectroscopy ever in your life. So, please remember that we should report the corrected emission spectra, not just simple emission spectra. Simple emission spectra means without that correction file, but we should report the corrected emission spectra. Let me show you the modern fluorimeter. This is the modern fluorimeter, right. I have this lamp, let me change the color because yes. So, here is your excitation light source lamp, here is your excitation monochromator. Now, you know what is the role of that. Now, this light is coming like over here, here is your sample, right, or you can put your quantum counter over here and measure the S lambda file. Once you will measure this S lambda, and that is fixed for this instrument, you do not have to measure it every day, right. You measure it and that you store it for your future purpose, and that is it. So, once you will excite your sample, that sample fluorescence can be collected like this way, right. Then you have this emission monochromator and you have PMT. But you notice here another thing is present. Here they used a beam splitter and have taken one part of this light and feed it to the reference PMT. Is written, can you read it? This is a reference PMT, or we call this a reference detector, right, reference detector. Let us now name the detectors. Let us name it as S1, let us name it as R1. How to name it here? R1, and it also has another detector over here for some other purpose, forget about that, let us name it as S2. So, here is my S2, here is my S1 and here is my R1, correct. Okay. So, now when you will going to measure the and is also clear at this point that to get the corrected emission spectra you already have generated the correction file, right. You already have generated the correction file is S lambda file, right, I just explained. So, you already have this S lambda file for correction. Suppose now you are measuring emission spectra, you put your sample over here and now you are recording your sample, right. So, what you can do? You can measure the intensity at S1 plotted versus lambda emission. That lambda emission will be set by this emission monochromator, right. You will set it, what is the lambda emission. So, you plot it over here like this way and you will get something like this, right, but this is not correct, you know. So, better you plot S1 into correction file, right, and let us name it as S1C. So, in the computer attached with this, so correction file is already present and what you can do, you can you can instruct the computer like that way, whenever you will measure the intensity at a particular lambda emission, you multiply with the correction file. So, you will immediately get the corrected intensity at each wavelength, right. So, better not to plot S1 by lambda emission, but S1C by lambda emission, right. So, let me delete here. So, let us plot S1 into C, right. So, this is the multiplied by the corrected file, right, S1C. Now, for example, you are this is for a particular lambda excitation, is not it. So, lambda excitation for this lambda excitation, right, for this lambda excitation. You will get this emission spectra and this is your intensity, you are very happy and for a particular concentration. Next day when you will come and you start measuring it, right, you have used S1C, next day different color, next day you come, you have used the same lambda excitation. So, this is the day 1, this is day 1. Next day you come, you use the same lambda excitation, day 2, same lambda excitation, same S1C by R1 you are plotting versus lambda emission. So, you should get the same graph, same dependence, same fluorescence spectra, but what probably it is possible that you will end up with instead of this, what you end up with this emission spectra, right. What is the reason? So, then emission intensity are different now. So, for the day 1 emission intensity is this much and for day 2 emission intensity is this much, that means there is a problem, right. So, the problem is that the performance of this lamp is not constant. The performance of the lamp is the problematic situation over here. So, yesterday probably the lamp was much brighter than today. So, the excitation light intensity is decreased today. So, that is why in day 2 you get a less intensity, because fluorescence intensity is directly proportional to the excitation light intensity, right. So, how to tackle this, right? There will be this fluctuation, I mean you cannot avoid that, right, for a real instrument. So, that is what you have this reference data R1. Some part of this excitation light, just a very little amount of excitation light is taken in the other direction and measured what is the excitation light intensity, is not it. So, instead of doing the S1C, if you now do S1C by R1, then whenever you will measure with this condition, obviously the concentration of your molecule will has to be same. So, in this condition every time you will going to get the exact emission spectra, right, including the intensity, not only the shape, but also the intensity. Although initially I said that intensity quantum yield is better than intensity, but sometimes you also need the intensity, right, for everyday life. So, while measuring the emission spectra, make sure that you are following this convention S1C by R1, right. Let us come to this another measurement, which is excitation spectra. I briefly mentioned earlier that excitation spectra is nothing but you keep the emission wavelength fixed, that is your detected emission wavelength, and scan the excitation wavelength and plot the intensity of emission at that detected wavelength versus the lambda excitation wavelength, and what you will going to get must be very similar to the absorption spectra. That is one of the property I said, right, earlier. Let us see how we are going to get this. So, in this case what you have to do is you need to fix, right, this. Okay, let me go to the next page. So, in this case what you need to do is your excitation mono your sample emission is coming, here is your emission mono and detector. As I said, you already have a reference channel over here. This is my reference detector, and I named it as, I named this detector as S1, I named it as R1, right, the simplified version of that complicated fluorimeter. So, in this case for the excitation spectrum, so here I have written for this, what happened, for this excitation spectra, what you need to do, you fixed the emission wavelength, right, at your choice, and then scan the excitation wavelength, and then what you are going to plot is the intensity of emission, right, at that desired wavelength where you have choose it, right, where you have fixed it, intensity of emission at lambda emission, that lambda emission is at your choice, right. So, whatever you have fixed over here, right, and versus lambda excitation, that will going to scan in the emission monochromator, right. So, here is your lambda excitation. So, in this case what you will going to see? You will going to see the some spectra like that way, and I said that this spectra is same as the absorption spectra of the molecule, right. Okay. So, either you can plot S1, the here either you can plot this S1. If you plot S1, what will happen? Let us see. If I just simply plot S1, then the emission intensity coming out of this sample is a function of concentration, concentration remains same. So, there is no concentration dependent, and is also function of excitation light intensity. And if you remember, I said that lamp is not ideal, right. That means, the output intensity of different wavelength coming out of the excitation lamp, here is my lamp, no? Here is my lamp. Coming out of this lamp is not constant, is not same, is not a horizontal line, right. But on the other hand, this looks something like this. So, this output intensity of lamp versus wavelength, this is nothing but this lambda excitation later on, right, is like this, right. So, when the lambda excitation is over here, obviously the fluorescence intensity will be small. When the lambda excitation is like this, then fluorescence intensity will be more, right, obviously. It also depends on the absorption spectra, that let me show. So, I said that intensity of fluorescence is proportional to the intensity of excitation light, right, and the concentration. If concentration remains same, then this is just proportional to the intensity of the excitation light, that means the intensity of absorption, right. So, IF is proportional to IA, and what is the proportionality constant? That is the quantum yield, right. How much, what is the rate of radiative transition over the total rate constant, right, over the rate of absorption, right, over the rate of absorption. If quantum yield is more, right, I will get 1 over here. If the quantum yield is 1, it is just directly proportional, that whatever the molecule you have excited, and that everything will coming back to the ground state by emission of radiation. If it is not, then some other factor will come. So, simply this is going to be IF is equal to phi f into IA. So, let me divide both side by I0, IF divided by I0 is equal to phi f IA divided by I0, right. So, this IA by I0 is nothing but I0 minus I by I0, right. So, this is equal to phi f to I0 minus I by I0, right. So, this is equal to phi f to 1 minus I by I0, right. And what I know? I know log I0 by I equal to epsilon CL. I also know log I0 by I is equal to epsilon CL is path length, right. This is the concentration, C is the concentration. So, here I can write this equal to phi f to 1 minus, right, e to 10 to the power minus epsilon CL, 10 to the power minus epsilon CL, right. I can write that. So, I can let me write it once again over here. Okay. Now, I will change the from 10 to the power to e to the power, right. So, this can be written as phi f to 1 minus e to the power minus 2.303 epsilon CL, e to the power minus 2.303 epsilon CL, right. So, e to the power minus 2.303 epsilon CL, I can write it as 1 minus 2.303 epsilon CL, provided that epsilon CL, that total quantity is very small, right. So, I can write e to the power minus 2.303 epsilon CL is equal to 1 minus 2.303 epsilon CL, provided this quantity is small quantity, right, provided this quantity is a small quantity. So, for small value, for small value, right. Epsilon CL is nothing but the absorbance, right, nothing but the absorbance. So, when the absorbance is small, then only I can write. Okay. So, then I can write it like this way, IF equal to phi f into 1 minus 1 plus, right. So, this is nothing but 2.303 epsilon C L, and I must have I 0, right. Where is my I 0? Over here, I have I f by I 0. So, once I write I f, then I must have this I 0 over here, right. So, I got this final equation. See here. So, this is just I have formulate that how the fluorescence intensity of your desired lambda emission will depends on these different factors. This I 0 is that excitation light intensity, excitation light intensity. This is your molar extinction coefficient, right, and this is a constant for a constant molecule, because that depends on the observed emission wavelength, right. So, this is fixed, this is a constant, this guy is a constant, this is a constant, this concentration you are not going to change it. So, it is a constant, the path length you are not going to change it. So, it is a constant. So, what I have, if the I 0, that excitation light intensity is constant over the excitation wavelength, then I f is proportional to epsilon, right. Epsilon means proportional to epsilon, I can write proportional to epsilon into C L, because C and L are constant itself. So, epsilon C L, so it is proportional to A, right. So, it is proportional to A, and that means this is my excitation spectrum, right. What you are going to plot is I f, right, this is the excitation spectra is proportional to A, right. So, this is excitation spectra, I will just write here excitation spectrum is same as the absorption spectrum. So, what I was telling here, if I now plot this S1, right, intensity emission and lambda excitation, these spectra will be equal to will be same as absorption spectra, provided two things. I have taken the concentration is low, if not, then I will not be able to write this one. So, concentration must be low, and secondly that this is most important. So, secondly is this, the excitation light intensity should be fixed over this wavelength, but it is not. You look here, you see here how to show you over here, but it is not, right, it is not, it is changing, it is like that, it is like this, it is like this. So, excitation light intensity I 0 is changing, right. So, what you have to do, you have to then use this reference detector. Now, if you do S 1 by R 1, that means you are normalizing the observed intensity as the S 1 detector with the intensity. That means you are somehow making this I 0 remain as a constant, just by putting this S 1 by R 1. So, this is also, please note that whenever you will going to measure this excitation spectra, and this is important, because if the absorption spectra and excitation spectra are same, it means that there is no structure change, there is no reaction taking place in the excited state. If they are different, that means there is a change in the structure of the molecule in the excited state. So, we every time need to perform this excitation spectra, right, and to see whether it is same as the absorption spectra, but it will never match if you do not do it like that way, that is S 1 by R 1, you have to do the S 1 by R 1, right, and also you need to take concentration should be small, right, small, So, concentration should be small, that is it. Concentration should be low. How low? The OD or absorbance should be in the order of 0.02, something like that, then it is applicable. So, today what I have shown you is that corrected emission spectra, how to get the corrected emission spectra and then excitation spectrum, and I have taken, I have introduced this reference detector, which is very important in this case, and then I showed you that under which condition this excitation spectra is same as the absorption spectra. And that is it for today. Thank you very much for your attention.